in my previous class, that was the first class itself, that pulse I define like that. Here is my 0, this width is in time domain is Tp, and that's how it is standing against time. And here is my voltage. So here is my, let us say, V. It is V from here to here, it becomes your 0 from here to here. This is also 0. This V is plotted like that. Okay, so that I have shown. I have explained what way this rise time and all that are coming. I'm giving one example, and I expect you to put your doubts or answers, etc. to that. Suppose I am having a pulse like this. Pulse train now I'm applying. Because switch is basically a capacitive effect. And all your computers, architectures, mobile phones and all that based on this kind of switches only. That's how it is coming like this. Here is my, let us say, 0, t equal to 0. It is coming like this. So you all know I have made it 0 to V only. It is a positive pulse. Okay, pulse amplitude will be constant here. It will here become a 0. It is repeating, and pulse width is Tp. Pulse repetition time is from here to here. Because the same phase of the pulse should come, so that I will call it a capital T as a time period. So that's how it is applied to control a switch. Okay. Now here I am giving one circuit. What is that? Here. I am making a circuit like this. This is resistance. This is a capacitance. So here is my input where the pulse is entering. Here is my output, and this output is going to this kind of control of the switch or something like that. So what is the output? Vt coming. This is the point where we do a lot of analysis. What way this Vt is coming? Yeah, I taken a simple example. I'll come up with some other examples also in due course of time. But first of all, so this Vt, I want to plot this Vt. Okay. Single pulse I have already explained. Now this is my R and this is my C. Where is that R coming? This is my R and this is my C. Time constant RC there. So what kind of pulse I'm getting? This pulse will apply here. It will come like this. Then it will come over here. It may vanish here. It may go beyond that also. I don't know. But at this point of time, capital T, another pulse has come. No, sorry. It's a high pass filter I have made like that. I'm sorry. This low pass I'm drawing here. I've drawn the high pass one. It is when I'm applying a voltage, that voltage is not coming immediately here. Whatever is coming, that is your 0. V or V not T. Let us sorry. This V not T. This V not T I'm plotting for RC combination, that is low pass combination. This V not T is for CR combination, that is high pass. CR circuit. Capacitor comes, it comes like that. Okay. So let me see, CR comes over here. Again it comes here. It will be symmetric because the circuit is not changed, pulse is not changed. Again it goes like that. This is my CR circuit. This RC I am plotting here. This circuit I am plotting here. That is starting from the zero, output is starting from the zero, exponentially rising. And after that it becomes constant. This constant is becoming what? V if we light, or it is slightly less than V, but not more than V. This V. This will be slightly less than V or equal to V like that. After that it is applied negative minus DC voltage. So here it will be going where? If it is less than V, it will get a tip something like this. If it is equal to V, it will be coming at 0. So it will be at 0 or less than 0. It will be coming like that. And that's what is coming here. Again it rises like this. So that a spike in the positive voltage direction is not coming if I am using this low pass circuit. I switch. Okay, again it coming here. It is coming like up to 0. It is not going to negate this direction. It is coming up to 0 only. And then
Sir, excuse me, the mic is mute.
can you hear me now? Am I audible now?
Yes, sir.
Okay, it's fine. So you have seen that. Then I also explained everything depends on this time constant. This exponential rise that you are showing. Okay. Every time you exponential rise only, or in this case, it is exponential decay. In case of your CR circuit, exponential decay. It is controlled by something e to the power minus t by the tau you are calling that tau is your r into c in both the cases. Exponential decay is this, and what about the exponential rise? Starting from 0, these were decay. is the exponential decay. Okay, what about the low pass case? It is rising also. Okay, so what is that rising? What is that? Here. What is the meaning of this rising? Okay, so this rising is 1 minus e to the power minus t by rc or t by tau, whatever name you give. This is one word. This is called time constant. Okay, so this is your rise. So here this thing will be multiplied with your input signal Vt into this. Here this one will be multiplied with input signal Vt. Okay, and this Vt will be rising according to that. This Vt will be decreasing according to that. So that's why at t equal to 0, in the case of exponential rise, it becomes your 0. I've shown you here, starting from 0, it is going like that. So at t equal to 0, it is 0. In case of decay, at t equal to 0, it is your V, amplitude of the pulse. Is the point clear? And then I explained that if RC, time constant, is very, very small, much less than 1, RC is much less than 1, okay? Like your some kilo ohms and microfarad, etc. you are taking, it is much less than 1. In that case, I explained it, same pulse train goes like this, okay? Here, when the pulse goes negative, it becomes like this. From 0 to minus it goes, it comes like this. When a time constant is small, this pulse that you are applying will be appearing at the output as this. You want more explanation? It's okay now. So if time constant is taken as small, you will be getting this kind of impulses, positive and negative both kind of impulses, and both the magnitudes will be almost alike. But if RC time constant is much larger than 1, you are getting one of these two. Else you are going for your high pass or low pass or whatever is there, you are getting like this. Here in both the cases, you are getting something like that. High pass, low pass, both the cases, time constant is very small, you are getting like this. So your switch will be now controlled by this kind of signal. You are giving the pulse at the input. So what kind of capacitive effect, low pass or high pass effect, that switch structure has got, according to that this will appear over there. Is it okay? Shall I proceed now? Some other direction? So basic circuit, I think Professor Sengupta has covered what e to the power minus t by RC, etc. are coming, and this is taught to you in your sometime class 12 also, and first year, second year as well, quite in detail. So that small thing I'm not taking. Okay. No saving. Here. Now coming to the average voltage now. I'm giving a square wave. Zero to V or whatever you are coming, I'm putting like that. I'm coming to the square wave. I'm controlling the switch with the square wave now. This is my, let us say, control signal. I'm putting as my ST or CT is better. CT is control signal CT I'm giving. Its magnitude is, let us say here I'm putting as V1, here I'm putting as your V2. Okay, here I'm giving a control signal. V1 can be negative, V1 can be positive, both, but I'll be calling it as a square wave, not as a pulse. Am I clear? If it is V1 and here is my 0, of course. So this kind of pulse is there from V1 to V2, this control signal you are applying, we call it as square wave. Okay? Now, when this square wave I am giving to high pass circuit, HPF, that means I'm putting here this is the output I'm taking, or V0T or CT, C0T, whatever name you give. This is applied to this. Okay, so what you will be getting at the output, there will be some average that will be subtracted. Okay, now here you are calling it as there are two timings here. Okay, one is here to here the width for your square wave that I'm calling as a TW, 0 to TW it is coming, and then there is off here from here to here. So this I'm calling as, let us say, T. Here T working, T is not working, so T stop and T working, I'm putting like that, TW and TS. Okay, so in terms of that, what your output will be controlled, what kind of width you are having, based on that it will come like this. So what happens, your V naught T will be nothing but your CT minus V average, and V average will it be constant or not? V average will be constant, it will not be a function of T. It comes as function of T in some other application, but here it will be V average will be constant. Okay, so CT minus V average will become your V naught T. And how much is my V average now? V average is your V2 going from where to where? Up to TW. Okay, then it is V1. He is operating up to TS. Sorry, I have written at TS here. Capital I have written there and very small both. I can make this also as a small TS. Okay. So V2 into TW, V1 into TS. This whole thing divided by capital T, that is TW plus TS. Okay, this will give you the V average. So in case of your high pass filter, what is the positive voltage? There will be two peaks. Okay, here there will be your V plus and there will be your V minus. Output will be fluctuating, sorry, minus only. So output will be fluctuating between this. If it is high pass, low pass, no problem. But high pass case, you have to be careful that how much a magnitude is coming at the control input for the switch. So V plus will be how much? that will be your V2 minus V average. And this one will be your V1 minus V average. So this one will be the two magnitudes between which the output of this high pass circuit will be appearing, high pass filter will be appearing. That will be at the controlled input of the switch. In that switch, once again, what kind of other mechanisms are there? We'll come to that. That way it is making. So if you look at that, what is the values? I'm writing the values also, you can check it. V plus is coming in whatever value you put, you can get the answer. That will be your V2 into TS. No, V2 is the TW, no, sorry. V2 into TW. V2 into TW, no. V2 into TS, sorry. I subtract it, it will be coming like that. That will be your V2 into TS minus V1 V2 into TW, sorry, what is the mistake? V2 into TS, one second, V2 into T2, V2 into T2 minus V1 into, oh yeah, V1 into TS, sorry, V1 into TS. So it will be your V2 minus V1 actually, and your V minus will be V1 into TW minus V1 into TS or no, TW only here again. TW, it will cancel, that's why I'm saying TW whole thing divided by T, this is whole thing divided by capital T. So V plus and V minus is coming something like that. What happens here? TW can come outside, TW by T, sorry, V1 again, V1 in TW, V1 TW. So V plus is V1, yeah. So TS by T, in case of this V plus, I have got TS by T, capital T, into V2 minus V1. And V minus I'm getting here as TW by T into V1 minus V2. Accordingly, plus and negative, positive, negative, this will V1 is smaller than V2, so it will be negative voltage here. Here it will be a positive voltage. So with this positive value to the negative value, it will be fluctuating. Average will be subtracted from there. It happens only in case of the high pass kind of architecture, that every contact point we consider as a capacitive effect. One series capacitor coming on the way, so it becomes a blocking capacitor, DC blocking. So DC is blocking, every average is blocked. And this is the amplitude of the pulse that is appearing at your this thing. You want a better diagram? I want a better explanation on new sheet or what? Understood it now? So CT was having plus V2 to some value plus or minus whatever magnitude is there for this V1. It is going like this. And because of this coupling capacitor, you are making like this. That is why for digital communication, whenever you talk of digital communication, you require a modem. Because otherwise the DC will be blocked and your 8-bit word will be shifted by that DC value below. So your 7 will be showing a smaller value than your the value 3. Okay, value 3 will be higher than the PCM code of voltage level 7 or so. So that's why we make digital modulation so that this DC wandering or DC blocking that can be avoided. So it is not your analog modulation, we go for a separate individual new modulation scheme, we call it digital modulation. Okay. Now, question, should I make a new diagram or it's okay? No query, no response. Okay, Professor Gupta, if I should go ahead now?
Yes.
It's okay now?
Yes.
I go ahead with something different now. I said it is all conceptual. There's nothing like any mathematics here. So the subject is just your understanding. What were DC, etc. monitoring taking place? I have explained that. Now I'm coming to this point. Operation of a switch. They all have taken from Millman and Top, that book we already having with you in your position. Here, this is my pulse. Now there is no conceptual error which we are having. Here the amplitude will be your V, pulse width your TUP, and it will be appearing periodically at a single pulse that I have applied and becomes your off after that. Okay, whatever is there, I will analyze a single pulse. It's the same thing, holds good for the periodic pulse train also in due course of time. When I apply this to a circuit, transit time I have already shown to you in the very first class. I have explained what is the transit time, what is the capacitor charging and discharging, that delay that you have shown. So here we have put our switch like that. Here is the operation point. Okay, this is my 0, this is my T. When I have applied here, from here to here, this is not your TP, this is something less than TP. TP is somewhere here. This is my TP. So it starts from this point, okay, and it will start building up, charging. According to that RC time constant, it comes over up to this point. Okay, it becomes constant. It becomes constant till what? Till this TP is there. Okay. Voltage has gone 0. It will not become 0 immediately, so it is coming at some other point. So up something beyond TP also, it is remaining at the switch operation point. These things I will make your explanatory. Here is the switch working as a memory, 1-bit storage, that kind of thing is going. I'm going to explain that. What is the switch has become a kind of the memory, and that has brought something like computer in the world, and that has made the revolution. All mobile phone, all computations and all that. Supercomputer is traveling on your palm top now. Okay, so to this point you are easily held up to this point. After that, it starts decaying because it has become so that negative voltage comes. So it will start decaying like this. It has gone up to this point, and then it becomes some voltage here. It may be zero, it may not be zero. Unless the next pulse arrives, it becomes like this. What do you call these things? Here, from here to here. Okay, this we call as response time. Sorry, not response time. Right, response time. From here to here, I call it a response time. And that's why several switches are coming, relays, your CMOS switches, nano switches, all these things are coming to control this response time. It should be as fast as possible, but it is practically having some time, response time. After the response time, it builds up to some voltage here, not fully. So this what? This is your 90%. 90% of the peak. Okay, and this is your response time. Normally we take here as 10% of the peak. So between this and this, whatever is coming, this point we call as rise time. It has not fully risen to the full voltage. Okay, 10% to 90% time taken by signal to build up, we call it rise time. Rise time is related to the even bandwidth also. That will be something, it will be covered in some other subject. Maybe I'll do it in the discussion or class also. So this is rise time. This is a response time. So don't confuse. After the rise time, it remains up to TP. It is remaining. Okay. It pulse is remaining. Now pulse is gone from here to here. So this thing, this timing, you can make a better diagram. I'm not very good in making diagram. This timing, that means starting from TP to once again, you can say this peak value, existence of peak value, TP to, you can say T dash, I'm calling here to T dash. We call this as storage time. So in every switch operation, there is some storage of the charge, storage time. Charge is stored, that means voltage across the capacitor is stored. So storage time, normally we call it delay. There is a response delay, there is storage delay. So still voltage is remaining at the switch. My pulse is gone, but it is remaining at the switch. Okay, then again 90% of peak. to 10% of peak. Peak value voltage I'm talking. This implies fall time. And with this weakness of the switching, we started exploiting various devices for storage of the charge for the time being, and that storage can be made your permanent, that we call it your stable state, or you can say semi-permanent, that we call it quasi-stable, or you can make it just after sometimes the storage vanishes, that becomes your unstable, or you can say a stable state. Okay, so based on that we started working out, and the revolution has come after this simple kind of your architecture. Is it okay? Switch operation has got timings like, I'm summarizing here again. First is your response time or response delay. Till that time, there is no signal at the input, response time. Second is your rise time. Like your CMOS circuits, they will operate at 3.5 volts. So if you are applying 5 volt, unless the rise time brings it up to 3.5 volt, switch will not become your on. It becomes on. After that, even the voltage builds up, it remains over there. Rise time. Then I come to this storage time. See, between rise time and storage time, there is one TP also. That TP voltage shows that my pulse has gone. The input control pulse has gone. Okay, so that is no more. After that, the storage time is there. Storage time. And then this is your fall time. So there is no confusion. Storage type does not start from TW. Before TW, it has built up like that. No, it starts after TW. Pulse at TP. Sorry, after TP. When the pulse width has gone, then it will start counting as a storage time. Till the pulse is remaining, that is not a storage time. That is because of the pulse appearance. No confusion?
No, sir.
Okay, it's fine. All are there. This got in as was first observed in the electromagnetic case, electromagnet case. Okay, that was called as magnetic memory, though it is not there in the syllabus, but few minutes, couple of minutes or 5 minutes or so I put on that. What was that? Same thing we try to bring in your this electrical switches also. So what happens? When you, this is my magnetic field intensity, magnetic intensity, okay, and then here is a magnetic flux. This is your flux. And this is your intensity. Our main focus will be on this magnetic effect kind of storage. How do you get in electrical system? And we will be analyzing all switches from that angle. How to make a switch according to that. And there are so many devices, components developed in the solid state also. How do you come to that? So it is like that. When you are increasing the current in the magnet, the magnetic effect will be changing. It goes from here to here like that. Okay? It has gone from here to here in this direction. Now the current is stopped or current is reversed. Okay? It will not follow the same path. That is the property of the magnet, electromagnetic. It is coming something like this. It is falling over here. And now it is going below like this. This is the return path. When I am reversing the current, the magnetic flux and this your intensity, this is the intensity becoming negative. I'm putting this as 0. So flux is positive, flux is negative, intensity is positive, intensity is negative like this. It has become like that. I have come up to this point. Now I change the direction of the current again. It will not go to 0 now. Understand? So negative flux remains there and goes slowly. It will not, H intensity will not become 0 at that point. It will be going like this. It will be going like this. Of course, on the final current is there, it will come up to this point. So that's what is your return path. Once again from here, if the current is changed, it falls like this. And in current increases, it goes like this. So this line in between, it was just when the system was excited with the current. Okay, so this center line is not repeated anymore till the circuit is not brought to a very kind of a ground state or so. All these things, effects are nullified. Only then it will come to 0 and again it will start like that. And all those times are coming over there. Now look at this structure. This was your plus H. This is your minus H. This is your minus B. And this side was your plus B. So it has got some points. What are those points? One is when this magnetic intensity becomes your 0. Let me point this first. This point is, just for the sake of definition, you remember, okay? This saturation. Saturation in negative direction, okay? In opposite direction. Opposite direction. Here again, your saturation point in the positive direction, or whatever say, saturation. So the saturation takes place at what point? That is your some value of your H. Okay, so we call this as your Hm, magnetic intensity at which it has become the saturation, and this one is your minus Hm, minus negative intensity at which it has got the negative, or you can say opposite saturation point, like that. Okay, this from 0 to the place where this flux has become 0, this we call as your how to write, I use some other color in that case, that is better. I'm using some other color, red color I'm choosing. Okay, this is the point I'm talking, from here to here. This I call it my HC. Okay, this is my HC. There is HC in this positive direction also, there is HC. So this is your minus HC, the second pole HC. The C I'm indicating here because that is known as your what is that? Coercivity, I think. Yeah, right. Coercivity. This is your, he call it coercivity. Okay, so flux becomes 0 at plus Hc, flux becomes 0 at minus Hc, but still it is not gone to this 0 state or something like that. That is remaining. That is coercivity, and this one is your reminiscence. This point where H becomes 0, Rm. Okay, H becomes 0, so this becomes Rm plus Rm minus Rm, like that. So this is your I call it here remanence. Also it is called a retentivity. Retentivity, sorry. Something like that. So this is the way it has worked. So now your what are the things? There is one plus Bm, positive direction. There is one minus Bm, magnetic flux, negative direction. Then there is plus Hm, that is your intensity, which becomes the maximum, where this flux becomes maximum intensity that it has traversed. There is your minus Hm. Then there is plus Hc, coercivity I'm talking, and minus Hc, of course. Okay, so these are the points of importance by which you are making like that, and something between 0 to this point. I put another color again. I take another color, green color here. Yeah, at this point, I'm talking of this point, 0 to this point where it is touching, where this intensity is becoming your 0, 0 to this thing. Similarly, from 0 to this point you are talking, that is called your BR. So BR will be your positive, there can be BR as negative. So I'm not putting this as a matter of the coursework, just I have given you this idea. BR we call it remanence. BR is your remanence. And HC is called as coercivity. Coercivity. So just for the information I given you this data, because initially the computers started with this idea only, and that was the switch. So this was also known as hysteresis loop. Hysteresis loop. Sys loop. This was observed in the magnet. So what happens if I apply a current and you come to this point, it remains in this state. Even that current is gone, current has become 0. When the current becomes 0, at that time it is traversing this path, but it is remaining somewhere in this region, in upper region itself. Okay, so even the current is gone, it remains around this only. Okay, now current has changed the polarity. It has not only become 0, it is not only gone, it has changed the polarity now. If it changes the polarity, it had traversed, it has come up to this point. After that current, negative polarity current is also gone, so it remains here. So when a binary signal, it was a positive signal, electric signal, or negative electric signal, this kind of DC was there, it was stored until unless the polarity of that signal was applied again in the negative direction. And that became a memory. So we call it 1-bit memory, 1-bit storage. 1 bit. Because when it became high, it got stored here. Even if that after that data is gone, it remained there. Now, when the data was applied as a negative, -1, 1-bit memory. Applied as -1, -1 was stored, +1 was erased from there. So it had got two stable states. One in positive direction, where the plus current was, plus voltage was stored. Here the negative electric voltage was stored, it was at this point. So it became 1-bit memory till the electrical disturbance was given, trigger was given, it remained there. So that's how the memory came. And 1 bit means you made it over millions, billions, trillions of the size of the memory nowadays. This is a magnet. We are working for the electric switches. Okay? I'll explore that in the electric switches. What were the solid state devices are showing you that. You are taking this with the help of some negative resistance value, sometimes with the help of some magnetic storage value. Or you can say electric storage value. RAM, we call it like that. ROM was just like a derived product. RAM was the original things. So that's what. Now I welcome there is question here. Otherwise we can, I think students are very few here, 169. Magnetic memory is not part of your subject, but other things I'm going to talk. Same two stable states And that only for the electrical devices only, purely electrical, there is no magnet in that. But the same hysteresis kind of loop we have to create, and then we'll be able to make the storage systems also. Okay, student side. Isita, do you have any question?
Yes, sir. Yes, sir.
Isita,
It's
Isita. See there, na?
As it
Fine.
went, maybe.
No, sir.
No, no question. Okay, I can see that. Okay, raise your questions, all of you. Okay. Fine. So next class I will be focusing more on this kind of switches, which you are realizing with help of MOS, CMOS, etc., etc. All those things are there. I will not go into devices detail. VLSI people will be dealing more in detail. I'll be talking of simple application of that. And remember, magnetic hysteresis are given as a reference. That is our objective. We want to make a storage. Until a disturbance is given, that should remain stored. Sometimes we change the state and we want, if the person has read it in between, that's fine, otherwise that should be erased. That is your quasi-stable state. There should be switching for that also. Okay, so that's what we are. Am I going at proper pace, students? Or you want something added materials with a higher speed, or you want me to be slowed down? Rosa Gupta
No,
is
sir.
okay, fine. Okay, Rosan, fine. So I think I'll need your correction on next class tomorrow. Okay, Professor Gupta, bye. Do you have teachers
Yes,
from
sir.
other places? Other places also? Teachers from other places? Patna Center,
They are
Jaipur
not
Center?
attending.
They are
Actually,
not
they are
there.
not attending.
Who is there?